Hi everyone, I'm Scott. I'm a physics teacher with a background in astronomy and STEM education research. Today I want to make a follow-up video to my previous question of what is energy. Last time we ended on a cliffhanger. I said that there are two definitions of energy that show up in physics textbooks that I actually think are wrong, but what exactly are they? So there's one thing that I just want to get right out of the way, and that is you might notice I look a little different from last time, and that's because I got a haircut. So in order to talk about the two definitions that are common but I think are mistaken, we'll have to go back to the definition we talked about in the last video. I argued that the definition of energy is A, it is a scalar quantity, B, it's conserved across a boundary in our universe, C, it comes in many qualitatively distinct forms, and D, it helps us predict the behavior of a physical system. So I really like this definition because it's what's called an operational definition. An operational definition is when we define an abstract concept in terms of something we observe experimentally. So for example, if we conduct a real-life experiment with a physical system like a pendulum or a spring, and suppose we measure something that doesn't stay the same over time, then we can conclude whatever we're measuring is not energy because it's not conserved. So the beauty is that this definition grounds us in observations, in experiments. Mathematical definitions are lovely and beautiful and elegant, but as a physicist, I think it's really important that our definitions are rooted in observations and equations rather than just purely equations on their own. So now that we've established my favorite definition of energy, let's look at popular alternative definitions. A lot of popular high school physics textbooks define energy as the ability to do work. So that poses the question, what is work? Well, there are actually two possible definitions of work. In order to explain the concept, let me tell you a story. So back when I was a little kid, I went to the local hardware store with my dad. There was a station where you could test out the new electric drills by screwing a metal screw into a wooden beam. So I picked up a screw, slotted it into the drill, and I drilled the screw into the wood. Now I wanted to see just how firmly the screw was held in by the wood, so I reached out and I grabbed the screw. And the screw was hot! It was blisteringly hot. I shouted and I yanked my hand away, and I got a big old blister for the next few days. So what happened? Why did the screw get so hot? Well, the answer is the drill performed work on the screw. Even though the drill was room temperature, and the screw was also room temperature, the drill still transferred a whole lot of thermal energy into the screw by exerting a force on it. Pushing the screw into the wood despite all the friction pushing back increased its temperature. So the first definition of work is as follows. It is the energy added to a system by means other than heat transfer. Now by heat transfer, I mean setting a hot object next to a cold object so the heat flows from the hot into the cold, heating the cold thing up. Work is basically the opposite of that. In the context of the hardware store, the drill was room temperature, and so was the screw. So I managed to increase the screw's temperature not by heating it up with a hot object, but by doing work on it. But here's the problem. Energy is supposedly the ability to do work, but we just said work is the energy added to a system by means other than heat transfer. So the two words appear in each other's definition. This is what's called a circular definition. It's not logical. Clearly, this cannot be the definition of energy and work because we're stuck in a loop. We don't need to panic just yet because there's actually a second definition of work. So the second definition of work is the force exerted on an object over a distance. So to give an example, suppose I push forward on a shopping cart. As a result, the cart now has kinetic energy, and the shopping cart zooms across the grocery store parking lot when I let go. I've done work on the system. I've transferred kinetic energy into it. So we say that the amount of kinetic energy I transferred into it is equal to the amount of force I exerted on it, F, times the distance I traveled while pushing on the cart, D. So in other words, we say that E, the energy added to the system by work, equals F times D. But that's not actually the definition of energy because things could get a little more complicated. So suppose I push on the cart at an angle, so a little bit down and a little bit forward. So now that the force is at an angle, we actually need to change the equation a little bit. Now the equation is work is force times distance times cosine of the angle between the force and the path traveled. In other words, W equals FD cosine of theta, where theta is the angle. And if we want to get really spicy, suppose I keep changing the amount of force I exert on the cart over time. So a little push, then a big push, then a small push again. Or suppose I push the cart in a path that isn't straight. Maybe I do some fun loop-de-loops. In that case, we have to use the equation work equals the path integral of force. It comes from calculus. If you're not familiar with integrals, for now all you need to know is that it's basically the sum total of all of the forces I exerted on a system over a given path. So this final form, that work is the path integral of force, is the most general definition of work, at least in my opinion. And so this second definition says energy is defined as the ability to do work, where work is the path integral of force. This definition is an improvement over what we had before because it's not circular, and some textbooks are content with this definition. But even though it's a pretty darn good definition, I still see at least 3 problems. The first problem that I see with this definition of energy is that it becomes very iffy when we try to apply it to vacuum energy. So in the previous video, I mentioned that we think vacuum energy is the reason why the universe is expanding, but it's really not entirely clear how you would do work with vacuum energy. So by definition, you can't take vacuum energy out of the vacuum that it's in. That's what a vacuum is. It's what's left over when you've taken out everything that you can. So in other words, you can't power a motor with vacuum energy, or you can't use it as fuel the way we use solar energy or coal energy. The point is, this definition just seems a little too simplistic. It doesn't really capture all the many different kinds of energy that's out there. The second problem that I see with this definition of energy is that even though energy is conserved, it'll never go away, one day the universe will actually be incapable of doing any work whatsoever. So as I mentioned earlier, when you mix together a hot thing and a cold thing, you end up with 2 objects that are the same temperature. In other words, the thermal energy of the universe becomes more and more evenly distributed as time goes on. And so if you zoom out and look at the whole universe, eventually, after an unfathomable amount of time, like this many years, the whole universe will have its energy be evenly distributed. The whole universe will be like a soup where all of the thermal energy is just evenly mixed together. There will be no cold spots, no hot spots. It'll all just be homogeneous. This will be called the heat death of the universe because there will no longer be heat to transfer from one region to another. So as a result, the universe won't ever be able to do work on anything else ever again. The whole universe will just be bland, tepid soup for all eternity. So on the one hand, there's still energy there because energy is conserved. But we won't have the kind of energy that we can do work with anymore. So therefore, the definition of energy can't be as simple as the ability to do work. There must be something more to it. The third problem that I see with this definition is a little bit more philosophical. So to me, defining energy as the ability to do work is kind of like defining money as the ability to buy pancakes. So it's true that if you want to buy pancakes, you are going to need money, and similarly, if you want to do work on a system, you will need energy. But that doesn't necessarily mean energy is defined by the ability to do work any more than money is defined by its ability to buy pancakes. In other words, even though the equation is true in almost all circumstances, except for the ones that we've just previously discussed, and even though it's a perfectly good description of energy, I would argue that a very good description is not the same thing as a definition. Defining energy in terms of work doesn't really capture the huge diversity and richness and far-reaching consequences of energy. It doesn't get at the core thing that energy is all about. So again, this is more of a philosophical point, and it doesn't undermine the truth behind the work-energy theorem. But as a physics teacher, I really want to get into the philosophy of the ideas behind the equation rather than just a useful equation on its own. And just as a final thought, we could actually imagine a hypothetical other universe that is a lot like our own, that also has a scalar quantity that's conserved across a boundary that comes in many qualitatively distinct forms and helps us predict the behavior of a physical system, but which does not equal the path integral of force. So in that other hypothetical universe, they would still probably call such a quantity energy, but this equation of energy being the force across a path wouldn't be true. So at this point, I want to pause and say that I hope I'm not coming across as too negative here. Because the truth is, even though this definition does have its problems, I think it's actually a mostly good definition that can be really beneficial for new physics students. Throughout the video, you might have been wondering, well, if this definition has problems, then why does it show up all the time in textbooks? And there's a reason for that. The answer is, defining energy as the ability to do work is accurate in most situations. In everyday circumstances, the kinds of energies that we usually see, like the energy stored in springs, or in magnets, or in the motion of an object, all allow the object to do work. You might have noticed that the exceptions to the definition that we discussed earlier deal with more exotic situations, like vacuum energy, the end of the universe, or a hypothetical other world where physics is different. So even though this definition is not perfect, it's still a useful and educational definition that applies to almost all of the situations that an introductory physics student is likely to see. To provide an imperfect analogy, saying that energy is the ability to do work is kind of like saying Italy has the shape of a boot. Obviously, Italy is not identical to a boot, and there are some pretty clear differences between a map of Italy and an actual boot, but it's an approximation that's close enough for some circumstances, and it can actually be pretty helpful to think of Italy like a boot in some situations. So for example, you might say Rome is at the knee of Italy's boot, or the island of Sicily is near the toe of Italy's boot. We refer to Italy as shaped like a boot because it's useful in some situations. Similarly, saying that energy is the ability to do work is a rough approximation that is mostly helpful in most situations. And if we want to get philosophical about this, I would actually argue that most of the statements that we hear in a physics classroom are just like this. They're not necessarily 100% accurate in every possible situation, but they're just generally true to the point that it's useful to think of them as true. A lot of modern physics is founded on the philosophical school of thought known as pragmatism, the idea that it's reasonable to act as if something is true depending on whether or not it's useful or educational in that particular situation. The ability to do work is a fine definition for an introductory class, and it only starts to fall apart when you look at the universe on cosmological scales. So there you have it. Those are the pros and cons of defining energy as the ability to do work. I personally prefer the definition we discussed in the previous video because it applies to more situations and gives us a more clear idea about why energy is useful in the first place. So the goal of this video is not to end the discussion about what is energy, but rather begin the discussion. Other physicists might present other arguments in favor or against the definitions discussed in this video that I didn't include. If you have a different opinion, or if you have some arguments for or against the ability to do work that I didn't discuss in this video, why not go ahead and discuss it in the comment section below. I'm really interested in hearing your opinion. Now, some of you might have noticed that at the beginning of the video I said there were two alternative definitions of energy that are commonly used other than the one I presented in the previous video. But in this video I only discussed one of the two. So there's actually a third definition of energy, one that shows up all the time in quantum mechanics. And it's a pretty fascinating definition because even though it's extremely abstract, it's actually the most mathematically precise definition of energy that we have. We'll be discussing the pros and cons of this definition and more in the next video. If you learned something today, why not leave a like? And if you prefer this animatic style of video, let me know in the comments so that I can make more of these. And if you're curious about the quantum mechanical definition of energy that we'll discuss in the next video, hit the subscribe button so that you'll be notified when I release the next video. Have a great day, everyone.